All right, good morning, everyone. I would first like to thank Abhishek and Sanjib for inviting me here. It's really thrilling to be on this beautiful campus. It's thrilling, aside from the beauty of this campus and the very nice weather at Bangalore and all the nice people we've been enjoying for several reasons. One is, I view you guys as the future of statistical physics in India, so it's actually kind of humbling to be able to lecture in front of you, and so I hope you'll get the best out of this. Second, this has been a very illustrious school. I've looked at the previous speakers in this one, and it's really humbling to be invited to be one of the lecturers in this series, especially as some of the current lecturers in this school, actually, I've admired since I was a graduate student and postdoc. One of them is up there, Sidney Redner, who has been my heroes in this during my entire career. And so I'm really humbled to be able to lecture in parallel to them. We've tried to kind of semi-coordinate a bit what we are going to talk about, so there should be some overlap. Hopefully that will work out and will be fine. As Abhishek was saying, please do interrupt with questions whenever that's necessary. We will ask to give Blackboard talks, which is great because it gives you a nice pace in proceeding. I think my lecture notes might be posted, so you don't necessarily have to actually jot everything down, although of course you're welcome to. But the downside of a Blackboard talk is you have to kind of live with our handwriting. Mine is not so great, my students tell me. So if you can't decipher any of the symbols and things, just stop me and shout. Likewise, I'm from Germany originally, work in the US now, so I have a funny German-US accent. If anything is not coming across and needs to be repeated, let me know, both acoustically and linguistically, and definitely on the content. Now, you're coming from all kinds of different places within largely India, and I see a few exotic affiliations too. So I assume your background's a little different. So I try to start what I think you've seen before, but if you haven't and things are too fast, stop me. If you're bored and you've seen all this, let me know too, because I can easily speed up, but that's not usually the issue. Okay, so please let me know how things are going. And yes, ask questions all the time, as interactive as that gets. It's probably as productive and optimal, right? Are we ready to go? Also, there's some tutorials. Will be around. I think we're still figuring out the details of how to run these, but whatever. I will be around the entire 2 weeks, so you can catch me during breaks, lunch, dinners, whenever, and please do so. If you're worried, you can also send me an email at my Virginia Tech email address, and I'd be happy to provide more information that way. All right, so I was asked to give a kind of set of overview lectures on critical dynamics. I actually wrote a book about this, so I'm trying not to kind of advertise that too much. This has a lot of kind of formal field theoretic treatment, which I've tried to talk about earlier in summer schools. It doesn't tend to work too well, so this time I decided to dispense with this kind of formalism entirely. But if you want to know about it, again, just catch me. So I'll just give you more the kind of phenomenological and scaling approaches and try to tell you more about the actual physics that's going on than the formalism. So on occasion, I will just have to tell you this is the result of the formalism without being able to go through the details. But again, if you want to hear about it, I can tell you more in private. So critical dynamics, historically, that is going back about 40 years or so when I was still in high school, addressed dynamics near a continuous phase transition in thermal equilibrium. So by that time, in the late 70s, the static equilibrium critical phenomena had been worked out quite nicely. There was scaling theory, there was the Ramanujan group, which just appeared in kind of the early 70s. And so there was a very nice understanding of thermodynamic and static properties. And then in the late 70s or so, dynamical properties were addressed. And so universal dynamic scaling near continuous phase transitions. And as we shall see, kind of the universality classes, they are split up depending on all kinds of things that are purely dynamic and not static. So that is what critical dynamics historically pertains to. Since then, we've kind of extended the scope quite a bit and included things like generic scale invariance in driven non-equilibrium systems where you got scale invariant behavior that is much more prominent than you might see in thermal equilibrium. So that would be applications for that would be driven diffusive systems. There's the scale invariance in driven interfaces, KPC equations, things like that, which we're going to talk about probably on Wednesday. And there's scale invariance in diffusion-limited reactions. Some of that Sid will address without the diffusion-limited, but scale-invariant behavior. And so we'll talk about that too. And then there are, of course, phase transitions out of equilibrium in driven systems, strongly non-equilibrium systems. And that also is under the general heading of critical dynamics. So roughly these three topics is what I'm going to talk about in these 5 lectures, and we'll just have to see how far we get. I will not talk too much about critical dynamics in quantum systems, quantum critical phenomena, because I think some of the other lectures will be covering that. But there is very intimate connections, and on occasion will point that out. So I'll be focusing largely on classical systems. Well, you know, superfluid helium is not really a classical system, but you can describe its critical properties, including the dynamics, essentially by classical theory. So I'll talk about classical theories. We won't see much of H-bar, and we won't see phase behaviors. Okay? That doesn't mean these concepts, as I just said, are not also important in quantum systems. They certainly are. So this is the scope. Any philosophical questions at this point already? That's not the case, so let's step back and go to kind of the 40s or something. And I'll probably, during half of today's lecture, just remind you of things about equilibrium critical phenomena, second-order phase transitions, continuous phase transitions, how to model those, what the basic features are, and how scaling theory works. So again, I assume at least some of you will have seen some of this, but it's a good basis to have, and we make sure that we all speak the same language. And then the second half today, I hope to explain to you scaling theory for critical dynamics. So critical slowing down and dynamic scaling hypothesis, things like that, and introduce some of the basic models, or relaxation models A and B, as they're called. Okay? So that's today's plan. So somewhat arbitrarily, I'm going to call today's lecture Near Equilibrium Critical Dynamics. And let's recall the kind of general mean field type description of continuous phase transitions. That is Landau's description. These days, we'd actually like to call things more continuous versus discontinuous phase transitions, because there's some ambiguities in first, second, third order. So it gets even more tricky out of equilibrium. So the second, first order, and so on, Ehrenfest classifications are kind of coming a little bit out of fashion because there's some issues. Okay? So let me just call them continuous phase transitions. And so Landau's idea, which is part of why he received the Nobel Prize, is to generically write down an expansion of the free energy density near a continuous phase transition in terms of what is called an order parameter, and for small order parameters, so near the transition when that order parameter is still small. So what's an order parameter? Order parameter is some, usually extensive physical quantity that you choose to describe the order in a phase transition. It's almost as vague as that, and there's a lot of art in choosing the right order parameter. You need to understand the physics of your system properly to pick the right order parameter. It's kind of really obvious in a ferromagnet. In a ferromagnet, you would choose the magnetization. So you have zero average magnetization in the absence of a symmetry breaking external field in the high temperature phase. So the order parameter is zero there. But there's spontaneous magnetization below the critical temperature, so you choose the magnetization as a useful order parameter. Likewise, for ferroelectrics would be polarization. It gets a lot more hairy already if you think about things like superfluids or superconductivity to pick the right order parameter. It's usually picked as, say, the superconducting gap of superconductors, or the magnitude of the superfluid wave function. So these are a little more intricate objects, and you really need to understand that there's something like gauge symmetry breaking in a superconductor. So picking an order parameter is already an involved business. Okay? But we, in this ansatz, already assume we've done that. We understand our system, we understand its basic symmetries, we know what kind of physical quantity is going to be distinguishing the two different thermodynamic phases. So we've done this hard part. And now we just write down an expansion in terms of the order parameter that I'm going to call S, for now just scalar. And I'm going to assume we have a S to minus S symmetry. So a Z2 Ising type symmetry, up-down symmetry. Okay? Yep, that's an assumption. So we just assume that, say, I have a magnetization and it's a scalar magnetization, so I can only have, say, Ising spins that point up or down. I'm assuming that a spontaneous magnetization up is equivalent in free energy to spontaneous magnetization down. That's an assumption on the symmetry of my system. At any given temperature, there are two most likely mean field values, correct? But I have that symmetry, and that restricts writing down the free energy density expansion for small s to even terms in S, because I'm assuming the symmetry. So this is where the symmetry enters into that expansion. So I'm going to call the free energy density F, and this function of this order parameter, I'm just writing down a Taylor expansion. Maybe I'll do this in the next line. So there could be a constant. Then the next term, if I have that symmetry, will have to be quadratic. And I'm calling the prefactor tau over 2. And then I have a u, and just by convention, put a 4 factorial here. Next order is fourth order term, and there might be higher order terms. So I'm assuming here that S in some sense is small. And then I could have an explicitly symmetry breaking field. So that's an external field that would break this up-down or C2 symmetry. And then the leading term for this one would be a minus H times S. Okay? Of course, I really don't need to worry about that constant, because constant shifts in free energy I can ignore. So let's just forget that. Those would be the free energy contributions of all the variables in the system that are not related to the order parameter, everything else. Okay. So I'm going to assume for a continuous phase transition that U is positive. If this coefficient happens to be negative, I have an unstable free energy and I need to keep going with the next order term, a sixth order term, say, for example. That generically takes you to a first order discontinuous phase transition. We're just not going to talk about this, but these are fun too. Okay? So I'm assuming U is positive. And then if I draw that, just because this is near the transition, right? So in the disordered phase, S is supposed to be 0. I'm going to draw a figure, will be explained that soon. In the ordered phase, S indeed has two possible values that are equivalent. And this expansion is meant to be close to the transition, so when the magnitude is small. This is not going to be valid all over parameter space. Correct. By choice of S. This is how we choose the order parameter. Okay? So yes, there's a lot of choices here. If your order parameter at the transition is finite, you just subtract that finite value. Right? So that's easy to fix if you misjudge that. But yes. So let me draw this Landau free energy as function of the order parameter, and happily we have colorful chalk here. So if I do this in a regime where tau, this parameter tau is positive 2, then I really just essentially have a parabola. And I'm ignoring, well, this is F0 here down here. Essentially, I have a parabola which picks up kind of fourth order nonlinear corrections for large values of S. And then the minimum of the free energy, the thermodynamic ground state, would just be down here, where S is 0. So that's the high temperature phase. And by definition, we just call that disordered. And that has to do because we expect at high temperatures entropy dominates. And so that's why we call it disordered phase. Now, if I look at tau less than 0, then I get a parabola that opens this way for small s, but then it gets corrected by a fourth order positive term. So ultimately, I get this to bend up again. I have to try and draw this. I'm not an artist, as you noticed, symmetrically. And so this is for tau less than 0. And then what happens is that this originally stable minimum in the free energy has become a local maximum. And I have these two possible values for my order parameter that are equal. This is all at h equals 0. That are equidistant from the origin, and that is indeed the two most likely values of the order parameter that you can have in equilibrium below in the low temperature phase. Okay. Now, if I had a vector order parameter, which is what you really would need for a ferromagnet, because the magnetization vector could point in any direction, then I would have to do vectors here. I would have to draw this as a function of a vector field. It's just a little hard for me to do on a board. And say if this is a two-dimensional vector field, you get a plane here, and you get a set of continuously degenerate minima in the order parameter. Right? You get this kind of Mexican head potential or something like that. And of course, this type of expansion is also very famous in quantum field theory and describes the Higgs mechanism and what have you. All right, so what happens right at the critical temperature, which is therefore tau equals 0. Okay, color for this, that's red. So the critical point is at tau equals 0 and external field 0. At the critical point, this quadratic term disappears, and all we have is this quartic parabola, so we get a very flat fourth order form down here. Okay. That's just the continuous transition that takes us from 0 order parameter to this phase transition with a very flat minimum down to these degenerate values. And these minima continuously grow out of 0 as I get away from 0 for tau, to negative values. So that's a continuous second order phase transition. Everyone good so far? Now notice that the curvature of these things has to do with the susceptibility or response function. And it's actually the inverse curvature, and we'll get to that in a bit. So here I have a finite restoring force in this effective potential that describes the dynamics or statics of my order parameter. So I get a finite response function. Same down here near these minima. Right? Basically, you can do a quadratic expansion, you get a finite response function. If I'm at the critical point, the linear response function vanishes. The curvature vanishes. The inverse linear response function vanishes, so the response is actually infinite. So you get very large response near that system. You mess with the system a little bit by some external field, it's going to go through large excursions in space of the order parameter. So there will be large fluctuations associated with that. Because in thermal equilibrium, response and fluctuations are intimately connected by the fluctuation response theory. We'll discuss that in a bit too. So we have to worry about large fluctuations, which is why I keep saying these are just the mean field, mean values of the order parameters. Certainly near the transition, you have to worry about fluctuations dramatically too. And that's the important part and the main story about critical phenomena. If I did have an external field, switched on, say positive, this would favor positive values of S. So what I would have is something like distortions of these parabolas, which would give me another minimum going down. In the presence of that external field, you then find a first order transition. But for us, this is the important bit to worry about. So with this, we can kind of identify tau as essentially describing the difference or deviation from the critical point. If you want to make this dimensionless, relative to Tc. Because if tau is positive, we are above Tc in the disordered state. If tau is negative, we are in the ordered state. And there could be some proportionality factor in front here that I'm not going to worry about. So I could now take this free energy and apply standard machinery, minimize it, compute the order parameter and what have you, to get its behavior as function of tau and h near the transition. I'm going to do a shortcut through that and just say it's obvious what the power law behaviors need to be by essentially just staring at this thing and looking at dimensional analysis, okay? Because I'm not really going to be worried about prefactors. So if, say, I wanted this spontaneous order parameter, that's at h equals 0, and we are kind of close to the transition but not at it. Small, not less than 1. It's actually tau negative. This is where we have spontaneous order parameter, and tau is much less than 1. Well, then I just need to look at these. H is 0, we forget this constant, and you see that s squared needs to scale as tau over u. Right? So s squared needs to scale as minus tau, and so s needs to be proportional to square root of minus tau. It doesn't require calculation, it's just how these things have to balance. And that already is some kind of power law behavior. We see that as we are going away from the critical point at tau equals 0 and h equals 0 into the ordered state, we get the square root growth of the order parameter, which is non-differentiable at the origin, and that's a singularity. Then we can look at the response function at fixed temperature. So that would be something like the mean S with respect to some external field at fixed temperature or fixed tau. And so again, I can actually kind of read the behavior of this off. If I now look at this term and that term, so this is the S by the H. S has to scale like S over H and tau. And so if I take one of these S's out and do T by the H, I'm going to get 1 over tau. And I will scale as 1 over tau with different amplitudes, but on both sides of the transition. So we are seeing indeed, as I was arguing with this picture, that as we get to the critical point, there will be a divergence of this susceptibility response function. Now this is, as I mentioned before, also via fluctuation response theorem, proportional with some factors of kT and what have you to the fluctuations in S, mean square fluctuations in S. And so those guys diverge too. Which means your normal thermodynamics argument where you say, well, fluctuations are extensive in scale like, chi. Chi is of order n, so fluctuations are of order square root of n. Relative fluctuations are 1 over square root of n, and the thermodynamic limit into infinity, you can get them. This is not going to work here. Okay? So kind of these central limit arguments or small fluctuation arguments are arguments that usually actually invoke a finite interaction or correlation length will not be working in the vicinity of a second order transition, and fluctuations will have to be taken into account. So actually we have something somewhat inconsistent here because we're assuming we can just look at the minimum, which is a mean field theory, or most likely value approximation, and we're seeing here that fluctuations are actually large. So somewhere not too close to the transition, that's kind of okay, but as we get too close to the transition, that's invalidated. We need to somehow fix that. Which is why it kept the statistical physics community happy for about 50 years and provided lots of research work to do, because that's a hard problem. I can plug this back into my free energy. So if I reinstate the constant here, just for the fun of it, if I'm in the disordered state, S is 0, and I essentially just get F naught by looking at the most likely values here. However, what happens in the ordered phase is, well, we just saw that the S squared scales as minus tau. So I'm basically getting a correction here that goes as minus tau. squared. So there's some constant and then tau squared. Right, so that's what you would have in the ordered phase. And then if you look at the corresponding specific heat, so that's like the derivative of the entropy with respect to temperature multiplied by temperature, but we need Tc, so that's multiplied with a constant, so it's like the S by the tau. S itself is minus dF, the entropy is minus dF by the tau. So this is actually proportional to the negative second derivative of the free energy with respect to tau. If you put this together, then we see that, of course, we're going to get value 0 in the disordered phase, and we get essentially that constant A in the ordered phase. As I said, if you go through the algebra, you can work out what A is. Anyhow, we're going to see a discontinuity. So if I plot these, what we're going to see as function of temperature is, for the order parameter, we're going to see this kind of square root discontinuity. For the response function, we have this kind of divergence. And for the specific heat, maybe let me put this over here. We are basically seeing a 0 there, then a constant there, and if you follow the temperature dependence, you find some linear behavior down here. So that there's a discontinuity in this region. We can also look at the critical isotherm. At the critical isotherm, we're sitting at Tc. We switch on an external field, a small one, and we want to know how what the equation of state is, so how the field is related to the order parameter. And you see if this is gone, H has to scale as S cubed. Or this thing scales as H to the 1/3. So we see these various power laws, and what these various power laws are the mean field values of more general critical exponents. You had a question? So in terms of critical exponents, what you would define is the specific heat might diverge at the phase transition as we approach tau with an exponent minus alpha. And then what we found is that in this theory, this approximation alpha is 0, indicating here discontinuity. This thing is in general called an exponent beta, and so we go as minus tau to the power beta, and we just found beta is 1/2. This generally defines an exponent gamma, so the susceptibility diverges as exponent 1/tau to the gamma, and we found gamma is 1. Critical isotherm defines a thermodynamic exponent called delta. So S goes as H to the 1/delta, and we found delta is 3. Okay? So it's a nice theory, but you actually almost never see these mean field exponents in experiment. They're close, but somewhat different. Right? So gamma tends to be larger than 1. Beta tends to be less than 1/2. Alpha is actually usually positive, so there is a divergence, not a discontinuity. And delta 2 is actually different from 3. And that's true also for exact solutions, say for the two-dimensional Ising model. So this is not right, and one has to fix that. Okay? That said, there's an interesting universality for these critical exponents. If I have systems with the same symmetry, same number of order parameter components and the like, do get the same values for the exponents. So for an Ising magnet or a liquid-gas transition, which are physically very different systems, and the origin of the phase transition is very, very different, you still find the same critical exponents in experiment. Likewise, for an XY magnet or a superfluid, again, the mechanism for the transition is very different, but they fundamentally have a kind of very similar symmetry. It's a two-component vector order parameter for the XY magnet. It's a quantum mechanical wave function, So a complex order parameter, which is equivalent to a two-component real order parameter, if you just take the real imaginary parts. For the superfluid, these things have the same critical exponents. But they're different from the Ising case. They're different from a three-component Heisenberg magnet. So that's the double challenge, to find out why these exponents are different from the mean field values and why they're actually the same for various systems. Okay. So as I said, I'm not going to walk you through the renormalization group that would actually tell you where these numbers come about, but instead I'm going to show you a generalization of the features we're seeing in that scaling theory, which allows for arbitrary values for these critical exponents, but also tells you how they might be related. Gives you non-trivial connections. So if we had worked out this in more detail, we would have seen that if you're in this regime here, this function f, if I evaluate that either in the disordered or ordered phase, is actually not going to be an independent function of the variables tau and h, but these values are intimately connected. So to look at the singular part of the free energy as function of tau and h, or small values of tau and h, which just means we are near TC, near the critical point. Then the general scaling form is this goes as tau to the 2 minus alpha. And then we have a homogeneous function which connects these, in general, independent exponents, but near the phase transition, they only show up in this power law combination with the general critical exponents beta and delta. So that means this is a homogeneous function, general homogeneous function. And these f plus minus things, these are regular functions as functions of the argument, but they would be different in the disordered and ordered state. So there's just different scaling functions, as they're called, in the disordered phase or ordered phase, which is what the plus minus indicates. So if I look at this, I can immediately get to the specific heat at h equals 0. So at h equals 0, this is assumed to be a homogeneous function, so that basically goes away. I do derivatives again with respect to tau, and you find this goes as tau to the minus alpha. So that was the definition of the specific heat, and we just constructed this free energy singular part to be compatible with that. We can look at the equation of state. So we look at the order parameter, which we would get by taking a negative derivative of the free energy with respect to the external field. You can kind of see that, get some exercise running back and forth. You can kind of see this here, right? So if I do df by dh, I'm getting s. And so if you do this, we have to take a derivative. H only shows up in here. We have to take a derivative of the scaling function. We get some f prime, and then we have to pick up a correction from the chain rule with another factor tau to the beta delta. So that's going to be tau to the 2 minus alpha minus beta delta, and then basically some f prime of the argument, which, as we then set h to 0, would just be the argument that's here. Now, in general, you would say this is tau to the beta, which defines the critical exponent beta. And so it tells you that beta has to be equal to 2 minus alpha minus beta delta, or it tells you that 2 minus alpha is equal to beta times 1 plus delta. So that is called a scaling relation. It tells you how the exponents alpha, beta, and delta are related to each other. They're actually not independent. Almost by ansatz here, you can see there's only two sets of independent exponents. One defined by the overall prefactor, one defined by whatever shows up inside the scaling function. Well, I can wonder about the critical isotherm. So how is that related to this exponent delta? Well, if I want to do this, I need to go back to kind of more general scaling form first here. And I want the critical isotherm, that's at tau equals 0. Right, so I have a problem here because in front of the tau to the beta, put this here. I have a tau. If I set tau to 0, that's not going to work. So I need to do an assumption on the behavior of the scaling function as I send the argument to infinity. Fixed, some finite but small h. I'm sending tau to 0, sends the argument of the scaling function to infinity. And its behavior in that limit needs to be such that as tau goes to infinity, the tau dependence cancels, because I'm not supposed to have a tau dependence at tau equals 0. So this scaling function needs to behave like its argument to the inverse power of delta. Then the tau dependence will cancel, and so this goes as h to the 1 over delta, provided that f prime of the argument x goes as x to the 1 over delta, as x goes to infinity. Right, so that tells me something about the limit of the scaling function. And then I'm recovering the critical isotherm with the exponent that we call delta, which is why that exponent in here was called beta delta. And then I can look at the susceptibility. So I need to do another derivative. This is supposed to go as tau to the minus gamma. That's another derivative from here. So it picks up another beta delta. And a little exercise that I think I leave for now. Same business as before, you found that gamma is beta times delta minus 1. So there are these two scaling relations. We had 4 thermodynamic exponents, so 2 of them are independent. So there's a lot of non-trivial information in this. And indeed, what this actually says, if I look at my system near the phase transition, it is thermodynamically scale invariant. I can look at various plots at various taus, various h, both small in the transition, but I can look this. And then if I rescale the x-axis in this form, multiply this factor into the y-axis, all I'm seeing is these 2 scaling functions. So I should get scaling collapse if I do this right way of plotting. And we're going to exploit that a lot. So I wanted to show you a striking example for that, from historical data. Complete intuition first. The Landau theory has that formative mean field exponents, but it was generalized, by the stroke of genius to this. The ultimate justification of this, if you do apply renormalization group ideas, you will get it. So you can derive it by that form. But it's a highly non-trivial thing to write. Just write that down. Not at all obvious. If you find that not at all obvious, good for you, because it isn't. All right, so here we are. So these are somewhat old data. Let me check how old. Somewhere from 1961, which is even prehistoric for me. And it shows the behavior of the specific heat near the superfluid transition of liquid helium-4. And there we are. So this is the behavior. It is not seeming to show you a discontinuous jump. You see this really strong spike, which seems to be indicating a divergence near this critical temperature, T lambda. It's sometimes called a lambda transition in superfluid helium because the specific heat looks like a Greek letter, capital lambda. That's where this funny name comes from. So this is this lambda transition. Okay? And so here, according to third law of thermodynamics, specific heat needs to go to 0 in a quantum system as temperature goes to 0. T lambda here is about 1.5 Kelvin. And then here it does something. And you get the strong enhancement, actually showing large energy fluctuations in the system near the phase transition. And then we can rescale this. So this, even in the 60s, they could look at this on a scale of millikelvin. So we plot the same data, kind of zoom into this strong peak, and this is what you're seeing. Even then, they could do microkelvin resolution. That's because superfluid helium-4 is nice and pure, and so they could do that at the time. And so now on the scale of microkelvin, another factor of 1,000, you get that shape. And in that regime, you can superimpose that plot onto that one just by shifting the x and y axis. Shifting the x and y axis is just kind of this rescaling. So there's this very striking thermodynamic self-similarity that shows up, but you have to be, in this case, kind of a millikelvin range near the transition. This one is not self-similar to this, but these two plots are. Now, these days, you can run these experiments on a space shuttle. Well, not anymore, but 15 years ago, you could run them on a space shuttle, and they've done this to even more resolution. Very beautiful experiments. So this is what this implies, not at all trivial. So we need to worry about fluctuations, which means we need to worry about a space extension of these concepts, and later space and time extensions, because we want to worry about dynamic extensions too. So we need to write down a theoretical description that allows us to worry about fluctuations in space. And that's going from a Landau free energy expansion to a Ginzburg-Landau free energy or Hamiltonian expansion. So we want to worry about spatial fluctuations. So we're changing our order parameter now to a space-dependent field. If it's a scalar order parameter, it's a scalar field. Let me generalize to vector fields. So this could describe magnetizations and the like. If you do worry about things like nematics and what have you, sometimes you do have to go to tensor fields as order parameters. So they can be arbitrarily nasty. If you do quantum field theory, these might be non-abelian, whatever, representations of some gauge group. Okay? We will not be worrying about this, but you can generalize this concept. So say this is an n-component field. I'm going to assume ON rotational symmetry, but that's an assumption. I'm assuming this is what my system is showing, not the most general thing I can write down. And then what I'm going to do is I'm going to write down, like the free energy expansion of the field. Let me just call that H of S for now. I'm going to drop the constant right away. I'm going to have a free energy density that is now going to be my vector field squared. Okay. I'm going to have a nonlinear term with the vector field squared and then squared. So that preserves nicely my rotational symmetry. I might have an external field in the business, and that's now dotted into S, where that dot is with respect to these order parameter components. So that dot is an n-component space, while this is a d-dimensional opposition space. But that's an order parameter density, so to get the order parameter, I would write down an integral over all space for that, for the free energy. That was the free energy density. So this is like a free energy density, a coarse-grained description that tells me how my free energy will depend on specific configurations S of X, and so what I'm kind of paying. So I'm paying for these terms by nonlinearity, and this is either gain or paying depending on the sign of tau. But I need to say something about what happens to spatial fluctuations. What is if my vector field S of X is not homogeneous and constant in space? I need to make an assumption. And the usual assumption is that you pay energy if you have deviations from a constant space situation. And then I need to write down a free energy cost for that. That accounts for that, but is still compatible with my rotational symmetry. And it's compatible, say, with spatial inversion symmetry. Another assumption. And then the simplest one you can write down is something like a gradient of all these S alphas squared. So that's a dot product in d-dimensional vector space. I'm being sloppy. I'm writing the same vectors for d dimensions and n-component order parameter. That's just because I'm lazy. Be sure these are different things. So if I want to be really lazy, I put this back into my vector. So that square is the dot product in terms of summing over all alpha components, and it's the dot product summing over components in d-dimensional space. Okay? So that's slightly symbolic, but I hope you can buy that. And paying for inhomogeneous variations means that this coefficient C is positive. If C is positive, I might as well dispense with it and call it 1, and just absorb a square root of C into S and rescale these. I can do this with one of my parameters, and it's conventionally done with that. So then this thing is Ginsburg, Landau, and in the context of using this for the RG, Wilson, effective free energy, or Hamiltonian, both of which are actually kind of wrong names. This is, this thing is not a free energy yet because we first have to do the mean, compute the partition function, get the free energy from there. It's not really a microscopic Hamiltonian either. It's actually kind of a coarse-grained version, mesoscopic version in between. Okay, which is why we kind of, in the literature, you sometimes see this called free energy, sometimes Hamiltonian. Both are wrong. It's something in between. Now we know that we don't need to worry about this. Okay, and then again, for tau less than 0, we have spontaneous broken speed. So if my vector field here is one component, that's the Ising model. It's a continuum description of the Ising model. If n is 2, as I said kind of before, it's the XY model or a planar magnet, or it could be a superfluid. If I wanted a superconductor, I'd have to add a gauge field describing magnetic field fluctuations into this one by minimal coupling. You can do that. That would give you Ginzburg-Landau theory for superconductors. We're not going to talk about that, so I'm not going to write this down, but it's a straightforward extension. N equals 3 is the Heisenberg model. 3-component magnet. N to infinity works too. You can do a formal limit of sending the number of components to infinity. If you rescale that coupling by 1 over n, you might have seen that, that's called the spherical model. So you can actually do the formal limit of that. And also curiously, you can send n to 0. If you send the number of order components to 0, you actually get self-avoiding random walks or self-avoiding polymer model. And that's not an obvious statement, but true. So this would be self-avoiding walks. Ginzburg's Nobel Prize comes partly from this, partly from superconductivity. This one partially led to Nobel Prize for Dejean. Okay, so this is not an obvious statement. I'm just telling you. So what does this actually mean? Arrived the boundary of what I can do here. So travel back, yes. So you cannot see that anymore. Yeah, I was just going to restart here. You guys over there, okay, with this side of the board starting there? Not that I'm aware of. But it's a great theoretical, free world tool because we can actually solve it exactly. But no, I don't think that's. Do you know of a real example, your physical example for the spherical model? I don't. That's theory land. So what does this mean? What this really means is we can assign a probability density to configuration S alpha of X by means of that Hamiltonian. That's what it means. Okay? So you write down some partition function which depends on tau and h, and then e to the minus this Hamiltonian over kt gives you the canonical equilibrium probability density to find that configuration. That is what this thing means. That means if I wanted to compute for some observable A an expectation value, what I need to do is I need to take this observable, which, since anything that happens in my system is described by these configurations as alpha, this thing needs to be a function, or rather functional, of these alpha, as alpha of x's. I need to take that value, this function of s, multiply with the stationary probability, right? And then sum over all configurations. And so that technically is a functional integral or path integral over all possible configurations of S alpha of x. Likewise is the partition function. The partition function, it shows up as the normalization. As usual, it's just the normalization. So I need to ensure that if I sum this over all possible values, I get 1. Or if I set this observable to 1, tells me that the partition function itself is this kind of path integral. Okay. And then, of course, you need to prescribe a way to do this. Now, if I discretize space, that's easy. I need to just take this as alpha at all positions and all possibilities, and for all positions, do this. I'd have to discretize, say, my gradient, because there's this gradient S in the Ginzburg-Lambda Hamiltonian, so I have to discretize it accordingly, and that couples different space positions. So that's one way of defining it. Another way is you go into Fourier space and then define the functional integral properly in Fourier space. The advantage of Fourier space is that you diagonalize the gradient term, so that just becomes a q squared, so that's easy. But then you have to worry about the nonlinear term that becomes that. Yes. So it's a sum of all components, actually product. Yes. So technically, this would be an independent product over all x's, over all components alpha of all this. Yeah, very messy object. Okay. So easy to write down, not easy to do. Right. Last one. Oh yes, sorry, this should be very true. This is just the exponential. I was getting too fast. Yeah, otherwise I'm doing weird double counting. Thank you for pointing that error out. Right in my notes, I was just getting lazy. Thanks. Okay. If you do this in Fourier space, maybe I just mention that. Fourier component, well, maybe I just write this down. So I can say decompose this into discrete Fourier coefficients. But then these S of Q's are complex. Right, so they have real and imaginary part. And then if you write down this functional integral measure, would be product over all components, product over all wave vectors, which I assume discrete here. And then I would get 1 over volume, all the real parts of this alpha of Q, all the imaginary parts of this alpha of Q. But I have too many degrees of freedom because it's a complex field, and the S of minus Q is the same of S of Q, because the S of X was real. So I need to restrain that to, say, the first component just to be positive for any of the components. You just need to take half of the all possible wave vectors, otherwise you just get a factor of 2 overcounting. Power of 2 of overcounting. Factor of 2 in free energy. But that's a slightly technical complication. Anyhow, so this allows us now to look at spatial fluctuations. As I said, I'm not going to walk you through too many technical details for this. But we can now write down a scaling assumption for correlation functions that is akin to the scaling theory for the free energy. And that is what we're going to need to generalize that to dynamic phenomena. So that's let me just write this down for laziness for a scalar order parameter. So that's a cumulant or connected correlation function. I'm subtracting the product of means here. So, and if you have a spatially homogeneous system, this thing is the same as that one. Translation invariant system. That. So this would be my correlation function that depends on, say, t minus tc position and could be an external field. And the scaling ansatz for this is that this goes as distance between those 2 points to some inverse power, which is usually written in this form, and some scaling function, which only depends on a characteristic length scale in the business that we're going to call the correlation length. Psi. So we have some interactions in the system that will typically induce correlations on the scale of the interaction range, something like that. So this wouldn't actually quite work for things like Coulomb potentials, because there the interaction range is infinite, and this, these scaling forms are also infinite. So this is for short-range interactions. Okay. But what happens is that as I'm approaching the critical point, we get these large fluctuations, and also associated with that large correlations. And so these large correlations mean that the typical correlation length as we approach the transition actually diverges too, with an exponent that's conventionally called nu. So correlations diverge near the critical point. So this actually goes with tau to the minus nu. So this is then roughly of the same form. We have an overall power law in front, which here defines how, if I'm right at the critical point, when psi is infinite, and therefore the argument here is 0, tells me how correlations decay algebraically as this power law of 1 over x to the d minus 2 plus eta. And it's written in this form because in mean field theory it tends to be 1 over d minus eta. That is d minus 2. So eta describes deviations from mean field theory, which is why it's written in that form. And then I have an argument inside these scaling functions, which again are different in the ordered and disordered state, that tells me how things depend on relative length scales relative to their correlation. Okay? Does that make sense as an ansatz? Again, it's a non-trivial statement because it means I can replot all possible data at temperatures kind of close to Tc, but at all kinds of various different temperatures. Once I translate them into this correlation length, replot all distances relative to that, and just multiply that, everything drops onto the same universal scaling function squared. A highly non-trivial statement. So if I look at this, I can get, like over there, I can get some scaling relations that tell me how this exponents eta and nu, which are kind of the fundamental exponents for these correlation functions, are related to these thermodynamic exponents. So then you can play the egg and hen problem. You can ask what comes first. In some sense, you could say that diverging correlations induce these thermodynamic singularities. Of course, it's not really causation. That is the way you want to look at things. So here's one example of how that works. If I'm looking at the limit of very large distances, these things should kind of scale like the back point there. So this should scale as roughly s squared, which is just tau to the 2 beta if I'm near the transition. That's kind of rough scaling. And so that tells me that if I look at this one and rewrite it in terms of, go to x to infinity, I need to make some assumptions in here. Or I need to make some assumptions that only give me temperature dependence. So I need to scale by these distances by xi. So if I scale this by xi and multiply by xi to that same power, xi only depends on tau. So I get xi to the power d minus 2 plus eta downstairs. That gives me a tau to the nu times d minus 2 plus eta upstairs. So if I look at this, this also goes as tau to the nu times d minus 2 plus eta. So equating those tells you that beta is 1/2 nu times d minus 2 plus eta. So that would relate the thermodynamic exponent to these correlation function exponents via the spatial dimension part here, almost by definition. Likewise, I can look at the singular free energy, which, if I'm somewhere near the critical point, should be dominated by contributions of size psi. It's a free energy density, so it should be dominated by correlation volumes of scale psi to the d. So this thing should be essentially looking like psi to the d. It's a density, so psi to the minus d, to get the signs right. And so this is tau to the nu times d. But that's also supposed to be tau to the 2 minus alpha, and so that would suggest that alpha is d nu minus 2 minus d nu. So that's another so-called hyperscaling relation that tells you how you get thermodynamic exponents from these correlation function exponents and involves that dimension. Now, just a warning, this is technically true only what is called below the critical dimension. At the critical dimension, you need to put critical dimension. So we get these relations. Next, we can Fourier transform them. And so in Fourier space, I have to apologize, the numbers of letters in the alphabet is finite. So that's not specific heat, that's correlation function. I used the same C for that before, that's just. So let me define the Fourier transform first. So I have the scaling form for C of x, which takes this form. So I do this Fourier transform, right? So if I do this, I'm buying, I do need to kind of make this dimensionless, so do an integral over qx divided by q, so it gives me a factor of q to the d. And that q to the d, I need to kind of have upstairs here, and rewrite in terms of that. So if I go through this and exploit this kind of shape, and we can talk about that maybe in more detail in the tutorials, this will take the form 1 over q to the 2 minus eta. So this thing changes sign because of this integral and this connection, and the d goes away because of this one, and I get a scaling form that now goes as q multiplied into the correlation length. So that's just equivalent for Fourier transform to this state. With careful bookkeeping. Correct. We could have called this thing Mickey Mouse, psi, chi, as it's actually, in growing interfaces, actually d minus 2 plus eta is called the wandering exponent or growth exponent. So there's all kinds of different ways you could call it. This one's motivated by the fact that in mean field theory or Landau theory, you find 1 over q squared. So eta is 0, Fourier transform that, you get d minus 2. That's the entire motivation. Yes. So everything you said is absolutely correct, and we could expand for that for the remaining 4 lectures if we needed to. So it's true. So where do the microscopic length scales show up? Let me go back to this, right? So this is a scaling form that's valid in the vicinity of the critical point. You go away from that sufficiently far, and it depends on the system what sufficiently far means. You get corrections to that. In these corrections, your microscopic length scales will play a role. So deviations, the next leading deviations from the scaling form will know possibly of microscopic length scales. That's where these things show up. But in the leading terms, they drop out. Not a trivial statement, but that's the fact. If you have long-range interactions, different story. Long-range interactions, effectively, you have non-zero etas to begin with. But yes, it shows up. You cannot avoid these etas if you do field rescaling, which you have to do in any randomization group approach. So that's where, of course, right? If you're less than 2 dimensions, this is actually, shrinking rather than, it's blowing up rather than decaying. And actually that tells an inconsistency in assuming there's a phase transition, things like that. That has to do with lower critical dimensions, I suppose. But, some of that is historic, some of it is actually meaningful. Meaningful is the two-dimension thing. How I call that exponent is arbitrary. So thanks for the extended comments, all very, very useful. This ultimately, let me give you 2 minutes. I say a little bit about the philosophy of the minimization group, and then we can get back to that. Remind me if I don't. But before we go there, I wanted to, I think I've said this. Right, so this is actually, again, by fluctuation response theorem. This is the same in equilibrium as the corresponding response function aside from a factor kt, which since we need to tc is just a constant. It's basically the same thing. And so that behaves like this also, right? But then if I look at the temperature dependence of that, I can do my rescaling thing. So I want to write this as a temperature dependence right at wave vector 0, which is the thermodynamic response, thermodynamic susceptibility. If I want set Q to 0, I need to make, again, an assumption on how these scaling functions depend on their argument. And they need to depend on the argument such that the Q dependence cancels. So this thing needs to go as its argument to the power 2 minus eta, so the Q dependence cancels. And so this needs to go as psi to the 2 minus eta. And so that's tau to the minus mu times 2 minus eta. But that was supposed to be by general definition of the thermodynamic exponent gamma that. So it also tells you that gamma is mu times. That was the last thing I wanted to say before I wanted to say something about the renormalization group. And that's just me to say that because it's to some extent a rephrasing of what you just said. So what happens if you try to understand it, I'm not going to go through this by means of the renormalization group, is what you do there is you study a theory at different length scales. Now those are microscopic length scales. There could be the cutoff in wave vector space, which is in the quote ultraviolet, so it's short distances. So you look at how the function depends on certain parameters as you eliminate, integrate out, do the partition function over short distance length scales or large wave vector length scales. That's because in that limit the theory is benign. The critical singularities show up at the critical temperature and field 0 as wave vector goes to 0, distances go large. That is when you get the singularities to show up. Not at large Q or small distances. That's well behaved. And therefore there you can do approximate theories. You can integrate out modes, you can do perturbation theory and the like. And then you get some effective scale dependence by rescaling the theory of your parameters as function of these length scales. That's fine. That's called general renormalization group flow. Works wherever, it might help you or it may not. But at a critical point, you have scale invariance. The correlation length diverges. So microscopic length scales don't matter and things are power laws. Power laws are scale invariant. So what you then look for in these flow equations is fixed points. Because these renormalization group fixed points tell you where your theory is scale invariant. Once you have scale invariance, ultraviolet and infrared is the same because all scales are the same. So what you learned in the short distance, large Q behavior in the ultraviolet translates back into what happens in the infrared, which is where the critical singularities show up. So the combination of knowing about scale dependence and scale invariance allows you to translate what you can compute in a safe regime back to the critical regime, which is the hard one. It's a non-trivial correction, but it allows you to do that. And that allows you to compute these exponents and show when and how they're different from the mean field value. Now, if I wanted to go through this in much detail, we'd again spend the entire. Yeah, so it's really in this business here of the Ginzburg-Landau Hamiltonian shows mostly up in this factor U. So let me digress a little bit and say a bit more than I wanted to, but that's okay. So there is, technically 1, 2, 3, 4 couplings. I said that 1 to 1, but it's actually there. If I set that coupling not to 1, I need to do something about it. If I do set it to 1, I need to rescale fields. So through absorbing this constant here into the fields, I have to worry about field rescaling. Let's do that. So it's 4 things. So what I see is I get away from the critical point through changing h from 0 and tau to 0. So at the critical point, tau needs to be 0, h needs to be 0. Left is basically field rescaling and this U thing. So once I do the field rescaling, I'm left with the U thing. I could write down more couplings, but it turns out the other couplings all scale to 0 under scaling towards the infrared. So they go away, which is a non-trivial statement. And then in the RG language, so I'm just waving my hands and telling you stories, is that this is called relevant, this is called relevant. These things explode as I go to larger distances. They need to because they qualitatively change the behavior from my system. At the critical point, I set the relevant couplings to 0. All irrelevant scale to 0. Leaves me with this one needs to go to a fixed point. Once that's at a fixed point, it tells me the origin of universality. All possible theories, doesn't matter what the initial coupling was, has the same asymptotic behavior. Then I expand near the fixed point. Look how these things go away from the fixed point, which is power laws. That gives me the critical exponents. This gives me 1. This gives me the second independent critical exponent. That's how it works. Does that make sense? Okay. That's kind of what I wanted to say about this. Not much more than that, because otherwise we're going to run in time trouble. And then what you do in the RG is, you do this perturbative thing, for example. There's also non-perturbative methods, but say you do a perturbative thing in this coupling U. That doesn't actually work because it's never small, okay? But it turns out that that fixed point value is of the order of epsilon, which is the deviation from what's called the critical dimension. So there is a critical dimension, upper critical dimension. That turns out to be 4, and you can get that from kind of power laws, just from scaling analysis and power counting and the like. And so I have a small parameter in my game if I'm playing near 4 dimensions. That's, theory land. Of course, we are not really in 4 dimensions. We cannot talk about quantum field theory. And, we would need epsilon 1, which is certainly away usually from perturbative analysis. Although you're kind of safe by the fact it's really epsilon over n, where n is the number of components, so maybe it's only 1/3 for a Heisenberg model. Also not great. But in this thing, you can do a formal expansion with a small controlled perturbative approach to things. And then you can compute, say for this Ginzburg-Landau model, these exponents, and so I'm just writing down some results here. This is the inverse exponent nu, and the eta exponent is n plus 2. So those are the leading terms you find in this analysis. And you see in mean field where epsilon is 0, so that's the mean field values, you get 0 here, and the inverse nu is 2, so nu is 1/2. And you see what happens, nu gets larger as I incorporate fluctuations, eta gets larger as I incorporate fluctuations, both of which mean that fluctuations amplify, in that case, these critical power laws. And in this case, the anomalous decay. If I take the limit of this one, look at the spherical limit, which actually, if I do this here, gives you the right answer, which is not obvious that it should, but it does. What you find is that 1 over nu becomes, this is just 1, 2 minus epsilon. And 2 minus epsilon is 2 minus 4 plus t. So that turns out to be just t minus 2. Eta is 0. That actually are the exact results from the spherical model. And that really incorporates the fact that you have a lower critical dimension too. The lower critical dimension tells you when a phase transition can happen. These systems with continuous order parameter cannot have a homogeneously ordered phase in dimensions less than 2 or into, right? So you get a spontaneous magnetization or a vector magnet, Heisenberg magnet, only in more than 2 dimensions. Right? It's lousy, of course. Yeah. So what you need to do is the following. A, the important part is not these values. The important part in these, A, you find the critical dimension. It tells you these things can be different from mean field values and in what dimensions that happens. And it tells you that these exponents only depend in D and N. No other microscopic parameters. They only depend on spatial dimension, symmetry of the order parameter, and if there were long-range interactions would depend on that. That's the important answers. And it tells you in which direction these corrections are going. All right. However, people have done a lot of work and done these epsilon expansions to, I think, 5th order or something crazy. And then you can do Borel resummations and do this carefully. Those fit very nicely to experimental values. Now that works for this Ginzburg-Landau model. It's not really been done for too many other models because we're happy with that. We just need one case where you show this is in principle doable. You want the actual critical exponents for the Ising model on a computer into it. Okay? So you want the actual critical exponent values to good approximation. Numerical methods are much better. Exact solutions are really great if you have them. These things are more kind of fundamental level. On what will the exponents depend? What direction are they renormalized into? Which directions take you the fluctuations? And what are the upper and lower critical dimensions? That's really what this is about. And to understand the origin of universality. Which of factors that you do include in your microscopic description actually matter and which don't. That is what this is. It can be, it has to be asymptotic. So we get a little sidetracked, but let me say that too. Right, so the convergence radius of any perturbation expansion U has to be 0, obviously. Because if U is negative, the physics is entirely different. Okay? So U to 0 is a singular limit. Convergence radius of this thing has to be 0. That doesn't mean you can't do an approximation that's useful. It just depends. And as I said, if you're in a large number of component limit, then this works just fine because the effective expansion parameter is actually U over N. So if N is 10, you're in luck. But otherwise, and as I said, that's not really the point here. The point of this is telling you which are the relevant couplings, which is irrelevant, what is the critical dimension, and which direction things are normalized. That is what you learn from this. Quantitative things for exponents. Okay. All right, 7 minutes. So I was hoping to spend half this lecture on statics. That was it. So the other half is 7 minutes, which means we'll just start with it, and I want to write down at least two few things, and then we take it from there tomorrow. Okay? Which is fine, by the way. I mean, I want to make sure you're following me. Everyone's still with me on this. Have I lost anyone yet? Okay, I think it's even shutting me down, which is fine too. Okay, then I do the other 5 minutes. Which will be fine because now I'm just going to extend this to dynamics, which is to some extent straightforward, but of course with hand waving and assumptions, which have to be. So let's see how we can extend that to dynamic behavior. Okay? So the first thing is just for the order parameter. What would we write down for the order parameter? Now, as function of time, starting from some initial configuration and then taking an average, which is not really necessarily an average over, canonical ensemble, but over something which we have to worry about when we worry about what the dynamics actually is. So it could be over stochastic trajectories or something like that. Well, we know asymptotically, as time goes to infinity in the stationary regime, this should go as tau to the beta. And so we can fix that by assuming, this really scales as function of time with a characteristic time scale. So this is like over here where we said things scale with distance and the characteristic length scale. So what's the characteristic time scale? Well, I get these large correlated regions. So I try to do an Ising model simulations. I try to flip individual spins. To flip an entire correlated region will take a long time. So there will be relaxation times or response times in my system that become larger and larger as I approach the transition. So there is this characteristic, typically relaxation time. TC, that I expect to grow as I send the temperature to Tc. And so my relaxation time diverges, becomes very large. That's called critical slowing down. It's a real bane of numerical simulations, because your simulations are going to slow down. You're just going to have a really hard time to get good sampling as you approach the transition, because your system just freezes on you. It's a mess. Okay? The typical scaling assumption for this is that goes as a power law of the correlation length. So as my correlation length diverges, the assumption is I get an algebraic behavior of these relaxation times with an exponent that's called the dynamic critical exponent. Z or Z, depending on, like the British or American alphabet. Okay. So since psi diverged as tau to the minus nu, this is also time tau to the minus c nu. So that's the dynamic scaling assumption for the order parameter. And it immediately tells me how the order parameter decays at the critical point as tau goes to 0 and time goes to infinity. With the same arguments I was making before, I need to have some assumption on the behavior of the scaling function on its argument that cancels out the tau. And so this ends up to go as t to the minus beta over c nu. So just by the scaling ansatz, you get the prediction that the order parameter at the critical point, starting from some initial value, asymptotically for large t, should decay like this power law in time. Okay? And you can look at that in more detail if you like. So let me translate that to a relaxation rate. This was a characteristic relaxation time. If I write down a relaxation rate, I would write down omega c and would say this goes as tau to the plus c nu, because it's an inverse time. Okay? Well, that allows me to more generally look at dispersion relations which depend on tau in Q. So you have some typical excitations in the system that depend on wave vector and on your distance from the critical point, and you would write down some kind of scaling function, here omega tilde, depending on your disordered or ordered state, where now you get q psi, because your characteristic wave vector should scale psi. So that's a generalization now and would give you dispersion relations. These same scaling forms are assumed, by the way, in quantum critical phenomena, which, this is taken over, and they've taken over this notation with this dynamic exponent. But then this is a quantum mode. I can translate that into Q dependence with the same arguments, right? So I want the leading Q dependence at the critical point, so when psi is infinite, I can see that this goes as Q to the power Z with some scaling function omega hat. And then this is the critical dispersion. So this length scale divergence, as how the relaxation time diverges with the correlation length at the critical point, translates into the critical dispersion going as wave vector to the power Z. That's equivalent statements. And then you can write this down in terms of dynamic correlation functions, and that's the last one I'm going to show you. As to C of tau, x, and t. And this would go, so if I look at the dynamic correlation function, which is really, say, time t here, 0, and time 0 here, then the static limit for this one is time 0. So in the static limit, I can do the same as we had over there, extract this overall power law in distance, and then write down all distances relative to the correlation length psi, and all times relative to this characteristic correlation, our relaxation time. So these are now scaling functions with two arguments, one in x and t. And of course, now I can Fourier transform that, write down dynamic response functions on the right. And instead of doing that, let me spend the last -1 minute to show you two more plots that illustrate how this looks like. Yes, so the question was, I'm putting out the X factor, not the T factor and things like that. That's arbitrary, you can do whatever. I could put out the T factor and rescale it accordingly, just with a different scaling. And we'll do some of this. I'll show you more equivalent forms of this tomorrow. You can do either of those. And in some cases, you do not actually have the, or the tau dependence. Oops, oh, we're good, leave it. All right, so here's one example for critical slowing down from experiment. This is actually showing the relaxation time in a easing ferromagnet in 2 dimensions. So it's an iron bilayer grown on tungsten, whatever. It has a critical temperature of 450 Kelvin. And they measured the relaxation time and did a log-log plot, and it's a nice power law with an exponent z nu that's about 2.09 in our language. Mean field would be 2. Okay, and we'll see this is described by what's called model A, so does the job quite nicely. You see that as in real experiments, at some point you have issues with statistics. So you get to too large values, you just have trouble, as you would have in simulations. So this is not necessarily an easy thing to do. And there's some thing about scaling function. This one. This is slightly exotic. That's a superconductor. High temperature superconductor, IPCO, yttrium barium copper oxide, in an external field at 56 Kelvin, shows a second order continuous transition, which they call glass transition. It's a vortex glass transition. This is the phase, this is the amplitude of the dynamical conductivity, and it's scaling, rescale all kinds of data for various different temperatures here, ranging from, I can't really see this, on a scale of about 10 Kelvin. This is the phase, 2 scaling functions after replotting things with appropriate exponents. These are the amplitudes. And here you can really nicely see how these different data points at different temperatures collapse onto scaling functions. And they're different in the ordered in low temperature and high temperature phases both ways. So that just illustrates this kind of dynamical scaling. And with this, we were diligent enough for today and opening this floor again for